Hey everyone, let's continue with the overview of the chapters. I aim to finish this in like the next dozen of hours, since I just want to move on to doing questions and reviewing previous chapters that I might have forgotten. So let's actually do a general chemistry chapter. So there we are. So we should be at General Chemistry Chapter 8. So now the GC8 is about the gas phase. We do have fluids in the physics as well, but let's start here with the gases. So we have an ideal gas, which is the theoretical gas whose molecules occupy a negligible space and whose collisions are perfectly elastic. So collisions are elastic and occupy negligible space. Gases behave ideally under reasonably high temperatures and low pressures. So ideally under reasonably high temperatures and low pressures. So we have standard conditions, STP, which is 273 Kelvin, equaling to 0 degrees Celsius, and 1 atmospheric pressure. 1 mole of gas at STP is equal to 22.4 liters. This is very important for calculations we might face in the future on the exam. And we have 1 atmosphere equaling to 760 millimeters of mercury. This is how high the mercury goes, equaling to that pressure. And 760 torr as well, and 101.3 kilopascals, and 14.7 psi. Different units for the pressure of the gas. Then we have an ideal gas law, which is PV equals nRT. P being the pressure, V being the volume, R being the constant as 8.314 joules per mole Kelvin, and T would be temperature in Kelvin. Be careful, in Kelvin, not in Celsius. We have density of gas, which is rho equals m over v, or equaling pm over rt. If you bring the rt to this side, you'll see that pm is the same as pv, and the rho is the density of the gas, its mass over its volume. Then we have combined gas law. So P1V1 over T1 equals P2V2 over T2, and it's constant. So combined gas law. Then we have Avogadro's principle. So N over K equals K, or N1 over V1 equals N2 over V2. T and P are constants in Avogadro's principle. In Boyle, the N and T are constant, so PV equals K, or P1V1 equals P2V2. In Charles' law, N and P are constant, so then if you remove N and P, you have V RT, so V over T V over T. In Gilles-Sachs law, N and V are constant, so it would be PT. So if N and V are removed out of the equation, we have P here and T. Forget about R. P over T. We need a mnemonic to memorize this, right? So mnemonic. For gas laws. Then we have other gas laws. So Dalton's law, PT, like the P of total, the rho of total, I think. Total pressure from partial pressures, yeah. So pressure of total equals the pressure of A plus B plus C. And another Dalton's law for partial pressure from total pressure. So partial pressure of A equals XA. X is the mole fraction of the total pressure. And we have Henry's law, which is the A concentration equaling KH, the constant, times the partial pressure of A. I think this is in moles, the concentration, right? And or the concentration over the partial pressure 1 equals the A over 2, yeah, whatever, KH. You have diatomic gases like N2H2O2 F2SCl2 Br2I2. They exist as diatomic molecules, never a standalone atom. Mnemonic: have no fear of ice cold beer. Have no fear of ice cold beer. Then we have real gases. These gases deviate from ideal behavior at low temperature and high pressure. At moderately high pressure and low volume or low temperature, real gases will occupy less volume than predicted by the ideal gas law because the particles have intermolecular attractions. Again, let's read that again. Real gases will occupy less volume than predicted by the ideal gas law because the particles have intermolecular attractions. Remember here, there was no intermolecular attractions and the collisions were perfectly elastic. So they didn't stick to each other. Now we see that with real gases, they actually stick to another. And at extremely high pressure, low volume, or low temperature. So that was for a moderately high pressure, low volume, low temperature. Now at extreme, we have real gases will occupy more volume, right? More volume than predicted by the ideal gas law because the particles occupy physical space. So they occupy physical space. And so in extreme conditions, it's about occupying physical space. But also with ideal gases, they did not. They took negligible. They occupied negligible space. And van der Waals equation of state is that P plus N squared A over V squared times V minus NB equals nRT. So we have the nRT on this side. It's only the PV here. So for the P, we have an N squared A over V squared. And for the V, we have minus AB. A corrects for attractive forces. And B corrects for volume of particles themselves. So B is for the occupation of space, and A corrects for the attraction. Now we have kinetic molecular theory, the average kinetic energy of a gas. So half of mv squared, 3 over 2 kBt equals that. Kb is 1.38 times 10 to the negative 23, and the units are joules over Kelvin. Higher temperature equals molecules moving faster. Then higher molar mass equals molecules moving slower. So you have root mean squared square speed, which is this speed, and the radical of 3RT over m. We have diffusion, the spreading out of particles from high to low. Diffusion, the movement of gas from one compartment to another through a small opening under pressure. And Graham's law is radius 1 over radius 2 equals m2 over square root of m2 over m1. Lower molar mass equals diffuse or fuse faster. And higher molar mass fuse or diffuse slower. What are these? These are the diatomic, 7 diatomic gases. Never, N2, have, H2, fear, F2, never have fear of, O2, ice, I2, cold is it Cl2, cold beer, Br2. Perfect. Okay, we can check that off. And we have here for the I'm sorry, I'm just yawning. So GC8 is done, but we can. So how long did it take us? Almost 30 minutes, the same thing. Ooh, we need to still, so like action items. Tutorial on thermochemistry to fully grasp it. For this GC8, that was GC7. For GC8, come up with mnemonics for gas laws and ask GPT questions for the different gas equations. We need to also do the Kepler questions. then we have left GC9. Okay, and let's go to organic chemistry. Organic chemistry 8. So now we have carboxylic acids. Okay, let me just go take a quick break and eat some breakfast, and I'll be right back. Peace. Let me just finish this actually. So carboxylic acids contain a carbonyl and a hydroxyl group connected to the same carbon. They are always terminal groups. So carbonyl and hydroxyl connected to the same carbon. They are always terminal groups. Always. The suffix is oic acid. The salts are named with O8. And dicarboxylic acids are dioic acids. The physical properties are polar and hydrogen bond well, resulting in high boiling point. They often exist as dimers in solutions. Dimers. The acidity of a carboxylic acid is enhanced by the resonance between its oxygen atoms. So, enhanced acidity enhanced by resonance between oxygen atoms. The acidity can be further enhanced by substituents that are electron withdrawing and decreased by substituents that are electron donating. So further enhanced by substituents that are electron withdrawing. So you want the electron, the H's, to go away from the the carbon, or whatever, like you call it, the central carbon. The beta dicarboxylic acids, like other 1,3 dicarbonyl compounds, they have an alpha hydrogen that is also highly acidic. Yeah, so it's highly acidic. There's hydrogen attached to the carbon next to the carbonyl, and alpha proton is the most acidic due to resonance. Alpha proton is the most acidic here. Carboxylic acid synthesis via oxidation. So we use KMnO4 and oxidizing agents, right? And we give a carbonyl to here, so we can make carboxylic acids with this. And then we have reduction of carboxylic acid that yields a primary alcohol. We have the carboxylic acid here. We add the H minus, like lithium aluminum hydride, and LiLAH4, LAH also, I think they write it. And the aldehyde is now isolated, and alkoxide ion here we get the the resonance from the double bond goes on to getting a hydrogen, and getting the hydrogen is reduction, so you're reducing the carboxylic acid, and you turn it into and you add like a hydrogen plus ion, and you get a primary alcohol. And this hydrogen ion attaches to the O minus, and that's how you get a primary alcohol. We have nucleophilic acyl substitution. So a nucleophile attacks the carbon, and the double bond resonance goes on to the oxygen, alkoxide ion intermediate, and we have the new nucleophile, and we get the substitution, right? This is a substitution. Then we have acid halide synthesis. So we have the carboxylic acid here. The SOCl2 is the agent, and it adds the the chlorine, and it substitutes it with the OH on the carboxylic acid. And with ether PBr3, we can add a bromine here. So these are acid halide synthesis. It's essentially a substitution, but since you're synthesizing acid halides, you are calling it an acid halide synthesis. Then we have reactions of carboxylic acids. So carboxylic acids can be made by oxidation of primary alcohols or aldehydes, or oxidation of primary or secondary alkyl groups using an oxidizing agent like KMNO4, Na2Cr2O7, K2Cr2O7, or CrO3. I don't know what these are called chemically. We can figure that out later. So this is also important. Primary or secondary alkyl groups using an oxidizing agent. Then we have nucleophilic acyl substitution. A common reaction in carboxylic acids is a nucleophilic acyl substitution. We saw that there. A nucleophile attacks the electrophilic carbonyl, opening the carbonyl and forming a tetrahedral intermediate. The carbonyl reforms, kicking off the leaving group. And then we have nucleophiles. Ammonia amine forms an amide, right? Amides are given the suffix amide. Cyclic amides are called lactams. This is hard. Lactams, cyclic amides. Then we have alcohols, which form an ester. Esters are given the suffix -08. We had -08 here as well. The salts you see that they are -08. So -08 here as well. And cyclic esters are called lactones. Not to mistake this with lactates or lactose, right? This is lactone, and carboxylic acid forms an anhydride, and both linear and cyclic anhydrides are given the suffix anhydride. Same thing, right? Both linear and cyclic anhydrides are anhydride. Okay. And then we have, so these were for nucleophilic stuff, right? Then we have reduction. Carboxylic acid can be reduced to a primary alcohol with a strong reducing agent like LaLH4. Aldehyde intermediates are formed, but are also reduced to primary alcohols. NABH4 is not strong enough to reduce the carboxylic acid. Then we have decarboxylation. Beta dicarboxylic acids and other beta keto acids can undergo spontaneous decarboxylation when heated, losing carbon and CO2. This reaction proceeds via a 6-membraned cyclic intermediate. So this reaction proceeds via a 6-membraned cyclic intermediate. And then we have saponification, mixing long chain. So decarboxylation, we definitely need to figure out more about it. Saponification, mixing long chain carboxylic acids, fatty acids with a strong base results. Strong base results in the formation of a salt we call soap. So soaps are salts. Hey, who didn't know that? And mixing long chain fatty acids, carboxylic acids, long chain fatty acids with what? With a strong base gives us soap. Soaps contain a hydrophilic carboxylate head. So hydrophilic carboxylate head and hydrophobic alkyl chain tail, just like what we have in our cell membrane. They organize in hydrophilic environments to form micelles. A micelle dissolves nonpolar organic molecules in its interior and can be solvated with water due to its exterior shell of hydrophobic groups. That's why soaps are solid, but still they can shrink by pouring water on them because of these hydrophilic heads. Micelle are polar heads, have no nonpolar tails. Nonpolar tails dissolve nonpolar molecules such as grease, and that's where we have the oil droplets. And we have amide synthesis. So you have amino acid 1 and 2 reacting, and the DCC. DCC gives us the dipeptide, and this is a not ester bond. This is a not glycosidic bond. This is a peptide bond, and a peptide bond is an amide bond, so you are synthesizing amides, right? And DCC is here what you use. And we have anhydride synthesis. So that's why when you get amide peptide bond, right? Amide synthesis. This is an amide. And then you have anhydride synthesis. So acetic acid is 2 of these, right? At 800 degrees Celsius, very high temperature, you get acetic anhydride. So you attach these to acetic acids, and you get acetic anhydride, and you have ester synthesis. So anhydride synthesis, ester synthesis. You have the SN2 reaction, which is the sodium butanate. It's 4 carbons, so butane. O8 is because of the thing being ester, right? And wait a second, it's a carboxylic acid, sodium butanate. So O8 is for the acid. The O8 part is the fact that it doesn't have the H anymore. It's just an ion. So you have it with Na plus, and this is an O minus. It attacks a nucleophilic. It attacks the carbon here with the CH3I, and the bond goes to I reacts also with Na plus, so it gives NaI, and you get through a SN2 reaction. And this is a direct reaction, right? SN2 is 1 step. SN1 has 2 steps, right? So you get methyl butanate, butanoate, and you have the methyl attached here. So ester synthesis is basically this O being attached to something else. That's when you get an ester. Perfect. I'll see you in the next video after my quick break.